and start the recording if you didn't already.
All right, hey everybody. So we're gonna do the stream and hopefully it goes okay. First time I'm trying something like this, so let us know if there's any issues with the audio or the volume or any of those settings. I'm going to be looking around multiple screens just to make sure everything's not on fire. So we're going to talk about performance and optimization today. I'd like to introduce you to Severin. He's someone I've worked with at 3 different companies in 2 different countries for I don't know how long has it been now, like almost eight-ish years. So I'll let Severin do a brief introduction about himself, what he's working on, what he's done in the past, and then we'll take from there.
Sure. Yeah. Hello, everyone. I'm Severin. I'm engine programmer currently at IO Interactive in Denmark. I've been engine programmer pretty much for my whole games industry career, which is roughly 12 years. I started in Austria, then went to Germany and Denmark, then Canada, and now back in Denmark. Previously, I was at Ubisoft in Montreal, from the big studios, and I guess the games that I've worked on, at least the games that shipped and that people might know, are Far Cry, Rainbow Six Siege, and Hitman 3 recently. And I guess the last maybe 5 years or so, my main responsibility was performance and optimization and everything related to that, including tools and all of that stuff.
All right. So what we're going to do for this sort of interview chat thing, it's not going to be super formalized. We're just going to just do a casual chat on the topic. If you have any questions, you want to ask something, you want to say something in the chat, go for it. I'll be reading it and conveying the information to Severin, and he can basically respond, or we can both react to whatever. So this topic is kind of one that is necessary in every game and every project that we work on. There's not that much information out there. Sort of the performance people it's a small community and everybody kind of knows each other a little bit, and there's not that much information out there. Book wise and resource wise, there's basically this one is a pretty common one, and then this is pretty recent. So they're both good introductions. This one's a lot lighter, and it's a good like entry level introduction to the field. It's more kind of an easier read and more applicable to maybe generalized gameplay, whereas this is a bit more in depth, maybe a drier read, but with a lot more in depth analysis and more kind of like low level architecture stuff. So yeah, the audio on Severin side has a bit of a reverb. I'm not sure what to do about it. I think what I could do is if it gets bad, let me know and I'll switch to headphones so that my mic isn't picking him up as well. And that might help the issue.
Yeah, let me know if I could do anything, but I honestly have no idea.
I think it's mostly on my end. I did a very well. I jury rigged a big setup to stream this. Anyway, so let's get going. So first question would be, what is the role of a performance optimization there? What is it that you are responsible for? What is your day to day, and what kind of stuff do you deal with?
Right. Well, generally, I guess it starts at management and their goals in terms of performance for the game. And I'm strictly speaking about performance in games, not like general application performance. So, for example, the company could say, hey, we will ship a 30 FPS game, or we will ship a 60 FPS game, or things, constraints like that. For example, in Hitman 3 recently, we shipped on PlayStation VR, and there we had a hard constraint to not ever miss any 60 millisecond frame for VR. Otherwise, there are nausea, health issues related. So the first thing would be that you need to know the constraints that you have to work with, because otherwise you can endlessly optimize and never reach a goal. So you need to know what you're going for first. Once you know that, then in essence, it's fairly simple. It's measure, 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 then optimize, and then measure again until you hit your gain. Now, the measuring part is, I guess, kind of the harder, trickier, longer part. There's usually a lot of manual work involved. In terms of me personally or other people that need to optimize their systems, they need to manually profile. So generally what I try to do fairly early or as soon as I join a project is to set up some kind of automated profiling, which means that basically the game runs somewhere on a server machine and captures profiling data. That is kind of necessary to easily catch regressions and also generally see the status of where the game is at, and specifically the actual build that may be shipped. Because obviously locally, I work on my locally compiled version with maybe local, slightly different libraries on Windows or other things, and I'm running on a fairly beefy workstation, which again will most likely skew the results that usually end users will have, at least on PC. Obviously, on consoles, there is just one platform, which is the nice thing about consoles. Like you optimize and run the game on one console, and you know it will behave the same on every console because it's the exact same hardware. So PC is always a bit of a pain, but yeah. So first thing is get something up and running that the game automatically runs, does various performance tests, and you constantly store and keep track of the data. The next thing is that obviously then you have a ton of data. Then you need to somehow visualize it or analyze it, because it doesn't help you if you have hundreds of megabytes or gigabytes of performance data and you don't really know how to analyze it. I mean, there's no point in opening a gigantic 100 megabyte text file and try to make sense of it. So you need some kind of performance tool graphs. There are tons of different tools available already, but also oftentimes I wrote a bunch of at least different specific plugins for what I was looking at. And once you have that, then, and I guess we'll go into more details later, but once you have the data and you have the tools to analyze the data, then you find the specific code parts that you need to optimize. And there's a little caveat there what that means. But you find those parts that you need to optimize, and then you optimize, and then you measure again. So basically, the most important part is never do anything without measuring before and after. I know that it's unfortunately fairly common, some gut feeling based optimization that I would say is fairly common in the mid range of programmers. So like the I guess dangerous half knowledge. They think they know what the issue is, and they heard like random people talk about, oh, it's a cache performance, a cache problem. Oh, it's a disk problem, and then they just apply optimizations that would fix this issue if it was the issue, but they never bother to check if it really is the issue. So they basically optimize into the void without knowing if that actually helps at all. And obviously, like experienced performance engineers will not do that. But I've seen it plenty of times happening that I see code changes. So, oh, optimized X, Y, Z. And I was like, yeah, but that wasn't the problem to begin with. So that optimization did nothing. Best case, worst case, it makes stuff slower or the code more unreadable.
So we'll touch onto the optimization and readability, simplicity versus optimization a bit later. So I think the main thing we'll start at the base level and then we'll continue. So you mentioned that you collect a lot of data, you measure, you track a lot of that stuff. What do you primarily like use in terms of tooling? And let's just discuss some common profiles out there. First question, what is a profiler?
Profiler is, in essence, just a tool that gives you metrics, however it collects them, about how your code behaves. Now, that's not necessarily just runtime performance, so it can give you timings for how long did function A take, how long did function B take, but it can also tell you, hey, you requested, I don't know, 15 gigabytes of data from the hard drive, or you're waiting for response from a network stream, all kinds of different things. And basically the profiler, all it does is it collects these data points, whichever you're interested in, and basically gives them to you in whichever format it chooses to store. For the collection part, there's generally two different ways to do it. That's instrumentation and sampling. Instrumentation basically just means that you program, for example, measuring you basically read the time, the current timestamp of the CPU or the wall clock time, and that is part of your program. So that code is actually compiled into the program, so it will always run and will always give you the timings.
So this is the basically where programmers will put a macro or something in a function that says, hey, I want a profiling scope here, or I want you to track this function, I want you to track this in a loop or whatever else.
Yes.
And this has a cost, usually associated with this approach.
Yeah, I mean, generally any kind of profiling has cost associated because things need to happen to measure the data. That doesn't magically appear. So even in sampling, there is some kind of overhead. It's usually lower than instrumentation, but there's always some cost there. And especially with instrumentation, you need to be very careful to not instrument functions or pieces of code that get executed very, very often, because then you have a lot of overhead. For example, if you say instrument your allocation function and then you have a simple loop that does nothing but allocate and does a little bit of math, addition, whatever, doesn't really matter. But basically you have an inner tight loop, and in that inner tight loop, you constantly query the timestamp. So you have a lot of overhead to query the timestamp compared to the work that you're actually doing. Actually, kind of a bad example in the sense that ignore the allocation, just have a tight loop with nothing but like one or two math instructions in there, and you put the profile scope into the loop. Then yeah, basically your actual work that you're doing is 1, 2, 3 additions plus reading the timestamp, which in that case takes a considerable amount of time compared to the work that you are actually doing. And generally no one would do that, but it can happen if you instrument a function that gets called very often and you're not really aware that that is happening when you as a user just call that function.
So you say it won't. It's actually funny because I've had exactly that happen multiple times with junior engineers that are just starting out with profiling. They will get the tool, and then like every new tool, every nail is a hammer. Once you get a hammer, every object is a nail now. So we've had that in the past where it's actually given bad information because what they did is they started instrumenting a function to figure out that it's slow, started adding this in a few inner loops, and ended up like skewing the data that they got. They said, well, this function is slow, obviously, because you see on the profile it comes up, but this function is really fast. But then you remove the profile scopes, and then time slice, the time amount switch, and this is something that they aren't necessarily initially aware of, because for them, a lot of the time, that profile macro, they don't know what it does underneath the hood. They don't understand that sometimes it's taking a string, hashing it, putting it into the right data table to record the time, and there is an overhead of this involved. And so that is something that people need to be aware of and be careful with instrumentation. And that's kind of a very important kind of gotcha that a junior engineer will hit. Sometimes even senior engineers, they might not notice. They just,
Yeah, I would say it's not necessarily juniors that are at fault here. If we want to say at fault, it can accidentally happen. Say you have a function and you instrument a function because you call that once or twice per frame, but then suddenly some other code changes, and suddenly that function gets called 10,000 times a frame. Then you have a massive overhead from that instrumentation that was put there for good reason, because before it was never called that often. So yeah, it can happen accidentally as well. So it's not just, oh, I don't know what I'm doing, I'm just gonna instrument everything. It's also, yeah, if usage patterns change, then that can easily happen. But usually that's also fairly easy to spot in the profiles when you look at them and you have a scope and suddenly you have hundreds or thousands of tiny scopes underneath. Then you probably want to check, so hey, is this supposed to be there? What's going on? Where's this coming from? And you probably want to remove it.
Okay, so instrumented is more of a manual user-defined profiling. So let's talk about sampling. What is sampling?
Yeah, one quick thing to instrumentation. It's not necessarily just that you have to hard code. So basically, you can also inject the instrumentation from the outside. Basically, you run your program and you say, hey, I want to instrument function A, but I don't want to change the code because it's already running. So you can, that's probably some people that use, I don't know, cheat engine or stuff like that. That's basically what these kinds of tools do. They inject code into the running executable. So you can basically just inject your timing code in there and it runs as part of your executable, but it's not in the executable per se. So the next time you run it without the injection code, you have the executable without the injection code.
So we have a question.
Yes.
Is the overhead only introduced externally to the scope being instrumented, or can it actually make the measured scope's timing results incorrect?
That specifically depends on how exactly the scope is implemented. So imagine basically you usually want to store information about the scope itself. For example, the function name. Otherwise, you can't track really where it's coming from. Now imagine that basically you have two things. You need to store the function name somewhere and read the timestamp counter. If you first read the timestamp counter and then store the function name, then you skew your measurement in this scope because you read the timestamp first and then you measure the string copy plus whatever else is going on. So you want to make sure that the last thing at the beginning of the scope is to read the timestamp, and at the end of the scope, whatever cleanup you have to do, you want to read the timestamp first and then do the cleanup afterwards. But yes, the overhead, if you do it like that, then the overhead is purely measured in the enclosing scope. If you don't do that, then yes, you pay for the overhead in the enclosing scope and the scope that you actually want to measure. So yes, you want to be careful there.
Great. So sampling.
Yeah, sampling is also a fairly simple concept. It's basically the tool at a certain interval basically interrupts your process, get us the profiling data, like where in the call stack am I currently. It get us potentially other information about, for example, like usually first-party profilers can do that. First party, I mean like the actual hardware vendors like Intel, AMD, their profilers. They can read specific registers from the CPU that gives you information about cache misses, branch misprediction, all these kinds of stuff. But yeah, basically it all means is, all that sampling means is you just regularly interrupt the process and gather whichever performance data you want to gather. Usually it's basically where in my program am I right now? And then you store it. And that requires no change in the executable, no other stuff. It's purely from the outside. Like usually the simplest example that can be given is, and I definitely did it before. I don't know if you did it before, but you have a program, for example, at startup, and startup is super slow, and you're just new to the code base, you don't know what's going on. So you basically just break in the debugger, look at the call stack, hit continue, break again, look at the call stack, and you basically sample where you're spending time while you're starting up. Obviously, you can't do that for things that run in a couple of milliseconds because you can't break and continue that fast. That's what the sampling profiler is doing for you. But yeah, in essence, that is what it is.
And in terms of like overhead versus, let's say, versus an instrumented profiler, how would you kind of compare the two in terms of how much overhead is introduced through sampling the program at, let's say, a high frequency versus running the instrumented?
I would say that's generally super hard to say, given there are so many moving parts involved. It depends how much do you instrument, and it also depends on how high is your sampling frequency. And for each sample, how much data do you collect? So it is super hard to say. Generally, rule of thumb, I would say sampling usually is lower overhead, but yeah, it is super hard. You can make instrumentation being less overhead than sampling if you just go crazy with your sampling rate and collect pretty much all the status that the CPU has. Then yeah, you're probably super slow.
Okay, and another dumb question for me. Where would I use one versus the other? What are the strengths of the instrumented versus the sampling and vice versa?
I would say like instrumentation I generally use for a high level to mid level overview to get maybe like the first three functions on a call stack in the frame graph, not much deeper, because then usually the scopes get very tiny and the overhead gets super high. But I basically use that to get an overview of what's going on in the frame and where are slow functions that I want to look at in more detail. Now, depending on how slow the function is, if we're talking, I don't know, maybe 4 or 5 milliseconds, then I probably would first add some additional instrumentation in lower functions or different scopes in there to get a more narrow view of what I actually need to look at, especially if I'm looking at code that I didn't write, which, at least for my day job, I would say 95% of the time that's the case. I just dabble around in other people's code, so I usually don't really know much about it. But I definitely use the hardware vendor sampling profiles that give me all the details about cache misses, branch misprediction, when I'm actually optimizing a piece of code, not the overall architecture, because otherwise there is no way to get cache miss information, stuff like that, in the instrumented code that just tells you, hey, function X took 5 milliseconds, and that's it.
So I think that's an important thing to mention is that, yeah, the one is more for a global overview of your frame. They have a lot of the instrumented profiles also have the ability to set custom categories, like saying, hey, this is AI, this is loading, this is the player, this is now your networking stack. So what you can do with that is you can kind of give them a different color, give them a category, and when you get your profiling data, you can quite easily get an overview of how much AI is taking for the frame, how much is player. And those kind of things can be very good at a very high level to kind of give you a bird's eye view of your entire frame. Also for occupancy of cores, you can kind of see, okay, I'm using roughly, I'm paralyzed, or I have big gaps if I've instrumented kind of well enough. But again, it's a very macro view of your frame. And if you want like in-depth detail, then sampling is definitely the thing to drill in deep and kind of see, okay, within a function, you get the full kind of like flame graph that kind of tells you, hey, this function was sampled 1,000 times in 1 second. And in that 1,000 times, these are the functions that got hit the most. And so these are where the hotspots are potentially. It can also give you a kind of higher level view of a function before you start drilling into the details of like cache misses, context switches, whatever you have there.
Yeah.
Now this leads us into the next topic, which is more the kind of
one quick side note there. So yeah, basically the instrumented stuff gives you a per scope information. And obviously you don't want to put a scope on every single line of code because that is prohibitively slow. Whereas in sampling, it basically squinky gives you the instruction that it's sampled. So it's not like, so, hey, I do a sampling right now. This is the function that you're currently in. No, it will tell you this instruction in that function is slow. But yes, conversely, you usually don't really, I mean, generally, you don't see your actual frame layout because the sampling profiler doesn't know any of that. Most of them allow you to inject tags as well into the sampling. So you will get a frame graph with the sampling data. But that basically boils down to you have to instrument your code again to get that information into the sampling profiler. Sometimes you want that. Sometimes you figure, well, I need this information. So if I have to instrument the code anyway, then why bother? Especially if you don't need this instruction is slow or these 5 instructions are slow. It's that function, yeah, I know what's going on there.
Yeah, I think the only time I inject stuff into a sampling is basically a frame start and frame end marker just to make the data easier to parse. So I know when one frame starts and one frame ends. That's about all I've ever done. Another funny thing that can, well, it's not funny. It's more like me being an idiot. Sometimes with inlining, here's like a tales from the trenches. You assume you flag something as inline the compiler, which again is a hint, and you expect it to get inline because it's a small function in the header. And so you forget about it, and all of a sudden you have a performance hit somewhere. You do a sample run, and all you see is that function name inside of an enclosing function all of a sudden getting called like 12,000 times, and you're like, well, this should have been inlined. So it's a good way to kind of judge what stuff's been inlined and not, depending on how you've compiled or what compile settings you have, just to kind of validate this. And then you do the nasty force inline hacks everywhere to kind of fix some of those situations. If you end up in those cases, it's primarily beneficial for debug optimization, which a lot of people don't do necessarily. Because
I mean, I would say that usually, and I guess in the normal or average case, the compiler does a decent job deciding whether it should inline or not. If you need it to inline or not inline something specific, don't assume anything, check the assembly. Otherwise, could be anyone's guess.
Yeah, but realistically, a lot of us are not checking the assembly. I think most programmers in the last 5 years don't even know how to open the view in Visual Studio even. So
that is fair, but yeah, if you rely on that for your code to to hit a certain performance target, you can't just guess and hope. You have to check. If you don't care, then, well, you don't care and you don't check. But if you rely on that is a small function and I don't want the preamble and postamble of the function call and all of that, then you have to check if you rely on that.
So this leads us into the next topic, which is metrics and how do you take that data from either either profile we've taken and kind of reinterpret it and present it. And one big problem that on every production we've been in, and you've been suffering with this at least as well on several productions, is somebody will come in, we're going to do a bit of a role play. Like, let's say I come in as not necessarily, maybe a less technical person on the team that needs to have an idea of where our performance tracking. Maybe I'm the tech art lead and I need to know what sections of the world are really bad in terms of perf. Or maybe I'm the producer and I want to make sure that we're hitting our targets. And, from week to week or day to day, if our targets drop from like 60 to 58, I need to know so we can, plan our optimization paths or react or adjust. So there's multiple questions in there. We're going to start with the easiest one. What are good metrics to track performance at a high level for a project? Let's say not as a performance engineer going digging deep, but how can I expose information to the rest of the team that there is a potential performance problem somewhere, or something to raise an alarm or to provide some data to people?
I would say and that okay, that slightly depends a little bit how your setup is. For example, at a previous company, we had automated fly-throughs through all the different maps and collected performance data. And there, basically, the output was all the frame times. And then I would argue that this is the information that you need, and you can't really chop it down any further. Meaning that since you mentioned, and I know what you're talking about, person comes to you and says, hey, I need the performance in one number. And I say, yeah, well, that's not possible, because what exactly should that number be? It again boils down to what is the goal. For example, let's say the goal is you have to be at a stable frame rate, meaning you have to hit every frame at 16.6 milliseconds, none above. I can't really give you just one number other than yes, it is always true, or no, it is not always true. But oftentimes I get asked, yeah, just give me the FPS. And that is a little bit of a pet peeve for me, because FPS is mainly marketing crap and not much else. Because it's basically, as it says in the name, you basically count the number of frames that happen in a second, and there you go. That's your FPS. It is always, by definition, an average. So you can have, let's say, 29 frames that take 1 millisecond, and the 30th frame takes, I can't do the math in my head, but let's say 100 milliseconds, then you would still be at 30 FPS. But the user experience is going to be terrible, because every 30th frame there's going to be a massive hitch in what you're doing. So never ever, for anything serious performance, use FPS. That's just not a thing.
So this leads us into the topic of microstutter a little bit, where that's kind of the result of this. If you just track an FPS number like this, you can average it out and say, well, over my run, my FPS is like 60, but my 1% lows are 50, and then I have quite a few frames over 60, but my average now is 60, but the experience is stuttery on the level of like every couple of frames I have a dropped frame, or I have a high frame, or I have a dropped frame. And if you have something like VSync on, this is even more painful, because potentially you will drop 30 FPS every couple of frames. If you're running it, trying to run VSync and you were at 60 and all of a sudden you get a frame that's like 57, it's going to drop everything down. That's something to be aware of by using FPS, and it's a big kind of. This is, I think, why a lot of like hardware reviews have moved away from using frame rate numbers. Even like tech journalism has realized this is a mistake, and so that they've now presenting 1% lows, 1% highs, and then the average FPS, and so that they present you a fuller picture saying, like, yeah, the average FPS is 200, but your 1% lows are like 50. Is that a good experience, or do you want your average to be 100 and your average lows to be 90? Which is a better experience? And that's kind of lost in a single number value. We have some questions. We're going to just jump off. How common in practice do you find a case where forcing the compiler to inline something it didn't want to is a big gain? Well, firstly, you can't really force it to inline. You can strongly suggest.
Yeah, I mean, if you absolutely want to guarantee, and even then you can't really guarantee, then you just need to paste the code in there. Because even force inline on Microsoft is just a hint. It's a very, very strong hint that personally I've never seen it not respect, but it's still just a hint. Now, excuse me, what exactly was the question again? Something about
Well, what's the case that if you force inline, let's say the compiler decided that, hey, this little function in the header, I don't want to inline it, but then you force it to be inlined. Is there a case that that usually results in a big gain? I think the essence of the question is, can you trust the compiler to inline for you, or do you have to sometimes go in and force it?
Generally, most of the time, you can trust it. The cases where I personally don't trust it, and where I absolutely make sure by checking the assembly, is, for example, if you have a inner loop, like your core algorithm, and for various reasons, let's say readability, you have it chunked up in like 2 or 3 functions just to have better readability, or whatever, you don't like big blocks of code. Say you split it out in a function. Now each of the function is super small. It doesn't do a lot, but you just split it out in a function. You definitely want to make sure that this stuff is inline for the most part, because calling a function incurs an overhead. It's not just that you jump somewhere else. It's that due to the way that the language like C++ works, and for good reason, there is some agreement upon how do you pass parameters, which registers are you allowed to use, which registers do you need to save, which ones do you need to clean up. All of that stuff has to happen for every single function call. So if your function doesn't do very much, you don't want to have that overhead, especially in a super tiny, tight inner core algorithm. So you want to make absolutely certain, again, after profiling or with profiling, that these functions are inline. And sometimes you have to basically force the compiler, because compilers are pretty good, but at the end of the day, it's a tool that uses a lot of heuristics and guesswork to do the stuff that it does. And sometimes it just doesn't get it right, because you as a programmer, hopefully, usually know a lot more about your code and what's going on. And yeah, I know, compiler, you don't want to inline here, but I know for a fact, if it's inlined, it's faster.
There's also like certain settings on the build settings that can affect the rules for inlining. I think the favor size versus speed is one that can potentially control how aggressively it inlines. The optimization flags obviously has some control over that too. What I found in many cases is, okay, again, this is me. I like to have my debug builds run fast. And so for a lot of my math functions where I know it's like a 1 to 2 line bit of math, I want that inlined, even in debug. I don't care that I don't want to call the function debug. I don't want to step in it. I just want that code inlined, and I want to guarantee it's inlined. And a lot of times with optimizations disabled, the compiler just doesn't inline certain functions that it may have, even if you have inline enabled. And so at that point, it's kind of a good way to guide it. This is, I think, why in UE4, like another question was that they've sprinkled force inline across the code base. I think it's to support the debugging case, because one of the primary ways you work with Unreal 4 is in the debug game target, where the engine is compiled in release, but the game is unoptimized. And so there, depending how stuff works, you might want to force it. They've also got a bunch of hacks that I'm not even going to touch about some of the things that they've done.
I mean, apart from that, I may be wrong, but I think at least Visual Studio also has a compiler option where you can tell it to inline marked functions even in debug. Also normal inline functions, not just force inline, I think.
Yes, there's an option to enable it, but in my...
But the question is if you want to generally enable that for everybody. So
even with that enabled, I still noticed that in unoptimized build, some functions just weren't inlined.
All right. Yeah, I mean, that could totally be the case. And the thing is, in theory, it can also just ignore your force inline, because it is just a hint. I've never seen it happen, but it's possible. Conversely, the compiler can also decide to basically make a function for you where you don't have one. But yeah, like most of the time, I would say for the vast majority, except for inner core algorithms, you shouldn't and don't need to care what the compiler is doing with the inlining.
Okay, so coming back to the performance metrics, have you had good experiences with automated performance testing? Like you mentioned that you had this automated fly through of the map tracking FPS. What's been your experience with those kind of systems? How would you, how would you build them? What are things that are important in those kind of systems? You know, just general thoughts on the topic.
Yeah, I mean, generally, I think it's insanely important to have that. I know it's not always easy to build it for various reasons, and depending on how the game works and what the game is, to set something like that up. But it's just insanely important to have that, because you can run that thing on every single build that comes out of the build system automatically, and you immediately spot performance regressions. Because if you work in your day-to-day job, most people, and even I, just don't have the time to check every build every single day, what's the status, because every now and then I have to do some work as well. So you want that information out there and automated, so you don't need to manually touch something, because as soon as you have to do something yourself or someone else has to do something, there will be downtime. Someone will forget, or it rots or something like that. You want to have this automatically, just like you have your basically your CI running that just compiles all the change lists. You basically want to have a performance CI that takes the build that is done and runs the performance test. And it doesn't matter if it's in a timely fashion or whatever. If you get the results half a day later or whatever, it doesn't really matter, because you know which build it was, and you can get the code and you just see whether there are regressions. And yeah, report more than just FPS. Don't do that. At the very least, report frame times for, I guess, the game frame and the GPU frame, if you have that. GPU, like performance tracking on GPUs is a bit, let's say, annoying. And also, I'm not a GPU expert, so I'll basically leave it at that. There are possibilities to do it, but I also know that not all profilers and not all companies have that possibility. But if you do, yeah, report frame times, at the very least, frame times for your frame and for your GPU. Obviously, you can then go nuts and report more and more and more data. What you or the user of that data finds useful. Like I remember, I usually for these automated runs, I reported a bunch more data, and sometimes the give me just one number person would say, hey, what is all that stuff? Remove it. It's like, no, because I actually need that data and I want it. And I know you don't care about it, but if you don't care, just ignore it.
Yeah, that's kind of the thing where I think it's important to note that performance issues these days are not necessarily just code. A lot of times you would have, you know, one area of the world that was working fine, everything was great, and then you'd have an art pass on it, and all of a sudden your render thread or your render times spike to like 30% more because they've put in like 25 dynamic, not 25, but like 100 dynamic lights and insane numbers of objects and whatever else. And those need to be tracked and also bounced back to the relevant teams. So having information a little bit more fine grained than, oh, the FPS dropped, which basically implies somebody has to go in, investigate, figure out, do a profile, figure out, okay, well, why did it drop? Is it code? Is it this? Is it lighting? Is it what's causing it? Having this sort of more fine-grained information is also kind of good at the high level, because if you notice that only one level has spiked, it's likely not a code issue. It's probably just somebody did something crazy in the data side. But if you have across the entire game a 10% increase, it's probably somebody, changed code in a foundational system. So it kind of allows you to sort of bounce the performance regressions to the correct team. It's also worth noting that it's good to have QA trained. Having a specialized QA that then understands to some degree the technical aspects and is trained to be able to capture performance data and track this. So if he notices, would you say it's safe to say that maybe dev QA is the primary target for this data more so than maybe programmers? Or
I would say that would be nice, but usually the primary user is going to be me as a, let's say, first level support kind of thing, because it requires at least some insight or experience to analyze the data and read it correctly. And usually, since mostly I'm the only performance guy, I just do not have time to train people to do that. I would love it if DevQA could just go through the reports, and that partly also is fault of the tools that requires so much in-depth knowledge for no particularly good reason most of the time. But yeah, it would be awesome if they could do a first pass on it. Apart from that, since you mentioned the tracking, the other thing that I would always do is not just automated runs on the server for a specific build, is have built-in tracking tools into the executable that basically whenever, generally anyone, but depending on your company, your storage setup, all of that stuff, but generally when QA runs the game and plays the game in a retail or in a properly optimized build, automatically in the background, I would run what I call spike detection, which is basically I say, hey, we have to hit 16.6 milliseconds per frame. If one frame is above that threshold, then dump performance data for the last 10, 15 frames, whatever, automatically. So they don't touch anything, they don't do anything, they just play, 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 and at the end, there is some performance data for me to look at. So, hey, this frame spiked. Why is that? What's going on there? Because oftentimes, especially with spikes, it depends on a certain view angle. You have to look exactly in that direction or at that thing. Or You have to have I shoot me, he shoots him at the same frame. Certain situation that you then afterwards, if you don't collect the data immediately, you have basically no chance of reproducing it. But you know the issue is there because it happened.
So something like running a, let's say, I don't know, instrument or sampling profile in sort of a ring buffer with a few frames, like constantly. So the game would always be tracking at least 10, 15 frames. And as soon as a spike is detected, it would just dump that out and then continue going.
Yes, I mean, pretty much that is more or less what instrumented profilers do anyway. I mean, okay, that's not true. There is two kinds. Instrumented profilers that basically just stream the data to a host application, and if there is no host application, then the data is lost. And then others that basically have a local buffer of whatever size, and that's a ring buffer where you basically constantly write the data into. And yes, you basically need something like that. You can also do it on the host application with caveats, like you potentially can't do that if you're running on a console because there is no host PC, stuff like that. So generally, I prefer these kinds of tools to be self-contained in the executable. But yeah, basically you have just a ring buffer of data, and then you see, hey, there was a spike, boom, dump it to disk, and QA just can continue playing without any interruption or whatever. Or yeah, you also don't want them, ooh, there was a spike, even if you have an on-screen display that shows them there was a spike. You don't want them to have to manually then interact, like push a button to dump or something. You want to have this completely automated.
And I absolutely agree, and yet I've never seen any company using anything like that yet.
Well, then you have to work with me again. In the
Because
last
yeah,
days,
I remember some of the horror shows in some places where it was like there was no profiling at all in the engine, and it's like you want to get capture, you have to manually now find an external tool, integrate it in, and instrument a bunch of things. Or like Unreal has Insights right now, which is their new instrumented profiling. I haven't really used it, but before that they had something called the stat system, which was so slow if you enable it that it basically was useless. If you tried to run it on a full game, you would tank your frame rate, which is why they now replaced it. Which is more, they have something like a telemetry or Tracy kind of setup. But yeah, having it automated is probably a really good thing. And I think on the consoles, you can even dump to disk. So potentially
oh yeah, I mean,
we can
again,
get the data
like
back.
in the last five-ish years, basically, since my main day job is performance engineer, yeah, like I come to a project, okay, where are the tools? Where's the automated profiling? Where is the auto dump? Oh, it doesn't exist. Needs to be here. That's the first thing that I do.
So let's move on. We're almost at an hour, and I'm not gonna keep this one too long today, because of the time difference. And let's talk about like some actual optimization problems. We can try to use some examples. Like the main thing that we often do when we try to optimize something is we look at a macro optimization versus a micro optimization. So can you give us an example of like what would be an example of a macro optimization versus something that would be a micro optimization?
Sure. I mean, so generally, I don't really use these terms per se, because for me, it's just optimization. It's just different kinds of things. Also, it's super hard where to exactly draw the line, but I think generally I know what it's supposed to mean. So correct me if that is not what you think it means. But so I would say the macro optimization usually is on a system level, and by system I mean, like, for example, the animation system, the AI system, the physics system, and basically whatever you do there in terms of algorithms and the general structure of what's going on. versus micro optimization usually contains a lot of staring at assembly code and then trying to get the best instruction stream out of the code that you have. Now, the reason why I don't know if that's what you mean with.
Yeah, I think I'm gonna maybe give a good example of that. Imagine you have a third-person shooter and you have covers, and you record all your covers in a giant flat array. And then every frame, your AI code says, "Oh, I need to find a cover to go to," and it goes to that whole array and goes bit by bit and says, "Oh, are you close to me? Are you the right type? Blah blah blah," which can be insanely slow. And there you would replace that with a spatial data structure like an AABB tree or an octree or whatever. And you would query inside of it saying, "Hey, give me all covers within 20 meters," and then you just check those. That would be a good example of a macro optimization. Whereas a micro might be, "Hey, my dot product function is being called 27,000 times in a frame, and it's written very naively without any intrinsics or any kind of platform specific stuff that can really heavily optimize this." Going in there and then tweaking that function, looking at the assembly, looking at the intrinsics, looking at, per platform, potentially optimizing it, and do that. That would be more of a micro optimization.
Right. Yeah. I mean, like, yeah, I guess you could make the distinction. It's just, I feel like, okay, let's say then you have a function particle system, whatever, and you have a bunch of cache misses, and you change the data structure to better utilize the cache. Is that then macro because you change the data structure, or micro because you optimize for cache utilization? So for me, like the macro thing, high level, is more like the actual architecture or design of the thing, like actually solving the problem rather than an optimization per se. I mean, it's kind of a split case, but yeah,
No, I
I feel
agree. And that's a good example. It's like, again, looking at a single function and optimizing that single function based on cache misses, maybe creating some new temporary data structures, scratch memory to order the data better for access or whatever. Those are kind of more, yeah, I agree. Those are more what I would also agree are micro optimizations in terms of optimizing a specific algorithm's runtime to be faster without effectively changing the core logic of it. Whereas a macro would be like, well, in the case of the covers, I need to actually rewrite most of my selection logic in terms of like functionality. Whereas before I was just iterating through a loop, which I could have then micro optimized and arranged the data properly, shrunk the data structure so it's more cache efficient.
Yeah.
And, we could have micro optimized that loop, which this is a pet peeve of mine. Sometimes people say, "This is slow," and they micro optimize a thing and they don't see the fucking big picture. And so I've seen that before where one game was storing all their covers in one flat array of like 100,000 entries. And they wrote some horribly nasty compression code to bit twiddle and get everything super small so that the iteration was super fast. And it never occurred to anybody to just write a fucking AABB tree to do the query, which would have been a macro optimization because it would have fundamentally changed the way the system was used and built and authored. And sometimes this is something that's kind of hard to do on. It's more of a conceptual problem I have sometimes with how optimization is treated. We sort of try to relegate it to people like you that are very kind of like proficient with the low level or experts in sort of like the hardware, the underlying systems, cache misses, profiling that. But we basically remove the responsibility from other programmers that are writing the systems. For the most time, they just write something, submit it, and not my problem, fuck off. Like the engine team will optimize. And then the engine team comes in and tries to optimize something that they don't understand why it was built that way. They don't understand the context. And so they're limited in what they can optimize without potentially breaking the game because they have no idea what this code does or where it's used, especially for gameplay systems.
Yeah. Oh, I mean, regarding that, I have some, I don't know if you want to call it tip or whatever, but Since basically my day job, most of the time I dig around in other people's code, sometimes without domain knowledge. Just yeah, it's slow. I have to optimize it. Time constraints. The original author doesn't have time. Whatever. I obviously don't have the time to become an expert in that domain. So I have to optimize within these constraints. And especially since I oftentimes don't really know what exactly it's doing, what it wants to do, and oftentimes I also super don't care. But that's why I usually, the first step when I optimize code that I don't really know about is making it possible that I can run the core algorithm side by side with a new replacement version. Because first of all, I can then immediately in one profile see the old and the new data without constantly changing back, filling around, blah, blah. And the other super, super, super important thing is I can run both algorithms and at the end compare that they're to the bit exactly the same in all situations. That way, I don't need to know if the result is correct, but I know the result is exactly the same as it was before. So at least if it was broken before, it's still broken, but if it worked, then it still works. And
That's actually super important. Like, thanks for bringing up that's the right way to do it, and I argue any other approach is dangerous.
yeah, that the thing where I brought it up because my pet peeve then a little bit is design patterns and all the craft, because I usually spend more, well, usually, let's say 50% of the time, I spend more time actually transforming the original code into a way that I can actually run a second version in parallel versus actually optimizing something, because it's such a convoluted design pattern, let's use singletons everywhere piece of code that, yeah, that there is no chance that you can optimize that without having in-depth domain knowledge, and you know exactly what's going on in every line, and you know what the inputs are, even though they're hidden through singletons and stuff. So I always say, no matter what you do, and first of all, optimal code per se doesn't exist to begin with. There's always something that you can improve. And I never expect anyone to write performance code or anything. What I always say is, please write optimizable code, meaning at least your core algorithm should be somewhat self-contained with clear inputs, clear outputs, and that's it. And no singletons, no visitors jumping around 15 billion times. That would at least make my work a lot easier.
It's not even just for optimization because I basically mandate this as well. When people write code, I want the simplest version, primarily because, at least at the gameplay level of things, you always need to architect for change. The code will always change. It will always evolve, mutate over the course of a project. You need to have it in a very simple way that allows you to, one, also do side by side work, not even for performance, but just for writing a new iteration to compare, because you want to do a better version of some feature, but you want to keep the original around to do a side by side comparison. And yeah, always a lot of times it's like, well, yes, this thing works right now. You've made a giant mess of things depending on things and circular dependencies and God knows whatever else. If somebody asks you to change it, can you actually change it? Never mind performance. Can you actually change the feature without rewriting the whole thing? And when the answer is no, then that's something that has to be taught, and even at just a fundamental engineering level, not even performance optimized, because generally if they write it in a very simple, adaptable way, half the optimization problem is solved, because then it's easy to take that data and sort of adjust it or restructure it or change it as needed. But that is sort of something that needs to be taught to people, or somebody has to. Unfortunately, I think with me and you, a lot of our best practices were learned through pain of having to unfuck things. I'll never forget that diagram you sent with the dependency diagram on that one project, which was literally just a pile of spaghetti. A lot of that kind of stuff comes in through pain, and it doesn't need to be that way. We need sort of leads and stuff that will push the industry towards writing more kind of flexible code. Sometimes that even involves using a design pattern. It's not like it's, oh my God, the stuff's always bad. It's like sometimes the design pattern can simplify certain, systems. But again, it's
Yeah.
use it where it's needed just to give you the simplest, most flexible end result. Yeah, I, I wish it was easy to just tell people, yeah, just do it the right way and everything will be great. But
No, I mean that the right way is sometimes there is no right way because there are multiple right ways. But generally, I say like make stuff as simple as humanly possible because it will get complicated by itself, even without you adding layers and layers of complication on top. That's why not make it simple for yourself and for your peers.
that's
And yeah,
super important. Like,
just for the record, no, unit tests don't solve that problem.
yeah, tests in general. Like, don't get me started on that whole thing.
I mean, for certain things, it makes sense, blah, blah, but in general, for random systems, you cannot unit test it in the way that I meant, that I can play the game and know every single input results in the exact same output. That you just cannot catch all edge cases with unit tests for random gameplay system XYZ. That's just not feasible and possible.
yeah. So we're at like an hour and 7 minutes. So I think we'll start wrapping this up. What I'll do is, if anybody in the chat has any questions, or any topics you want Severin's like to answer or anything like that, just feel free, like post them and then we'll answer quickly and then we'll wrap this up. So I think there's a bit of a delay on the stream, so we'll wait a bit to see if people type anything. But yeah, it's been an interesting almost a decade of fun discoveries and cleaning and fixing and optimizing and I don't know. One thing that always bothers me is that we tend to lately it seems more common with programmers that people are like, well, I'm not technical, so I let the engine team optimize my thing, or I don't know anything about performance or how to capture or how to profile, how to do this. People are becoming very kind of specialized, and I try to, at least with my team, push them in a direction where I need everybody to sort of be a bit more generalized in terms of I need every programmer to know how to do a capture, even if it's just like with telemetry. Do a capture, take a look at the values, and if you see something weird, flag it. Make a Jira task saying, hey, this thing is slow, we probably need to do an optimization pass. So we know about it. Be able to, one thing that's important that a lot of people maybe don't do is there's that quote, right, that's always been taken out of context, that premature optimization is the root of all evil thing.
Oh my god, yeah, don't get me started on that.
Yeah, so that's a pile of shit. Like, yes, there's some dangers. If you start writing intrinsic based, super unreadable, micro optimized code initially, yeah, it's bad. It's unmanageable, it's unrefactorable, everything. But that doesn't say don't think about your data and your data structures and build something that in advance there's probably you can solve most of the fundamental performance problems in advance if you just thought about your use cases. So let's say I was writing a particle system. You'll laugh at this one. So I was running a particle system. I will expect to have millions of particles at one in a frame. So the first thing I do is I make a class called particle. And then I do a function called virtual update particle. And that's the foundation of my particle system. Now, that's a very idiotic thing to do if you're building a particle system, right?
Yeah, that's broken out of the gate.
Yeah, out of the box, that is the stupidest possible way to do it. And that's where I think that quote is important. It's like, yeah, that's not a premature optimization. That's just frankly almost common sense. The problem is that
that's
common
basic.
sense comes over time.
That's the basic design architecture. Solving the problem is what it is. That has nothing to do with optimization.
Unfortunately, people will argue that saying, well, it works. Right.
Yeah, I mean,
I can do it and it works and I get my 10 particles and they look great and everything's great. And then I scale it to 100,000 and I have 0.5 FPS. Or my frame time is 3,000 milliseconds, you know?
Yeah. I mean, that, and the other thing is, I mean, what I miss a little bit is back of the envelope calculations from people. Like, you don't need to be an expert in anything. Just like use super rough numbers. Like, let's say I want to update a particle, and let's say it's the simplest thing, no collision, no nothing, just a velocity position update. Let's say that's maybe 10, 15 instructions. Let's say an instruction is, who knows, 5 cycles. I mean, it's not what it is, but you just do a complete guesswork. And then you take that, okay, multiply that by 10,000, whatever, and you come up with, I just didn't remember my own numbers, but let's say 500 microseconds. And then you run the particle system that you actually wrote, and it takes 5 milliseconds. That's an order of magnitude slower. So something is wrong here. Either you were completely wrong in your assumption, or you're solving a different problem, or you botched something completely in your implementation of that thing. That doesn't mean that it's fast or slow for like the guesswork that you did. But I feel like people don't even understand how fast computers are these days and what's possible. I always shudder, and that is, I guess, throughout the industry, because Adobe Flash and all of that stuff. But when I see that we render hundreds of thousands of polygons per frame in 60 milliseconds, and then the stupid Flash update for UI takes 60 milliseconds, there is something wrong here. Fundamentally wrong.
There's a caveat to be said there, though. What you said is that making that back of the napkin math, I agree, but you need to always profile just to validate, because that gut experience, you have it because you've had years of experience, but some people just don't have a gut feeling for how long things should take. And that you have to sort of build over time by measuring, kind of getting a feel.
Sure.
Because like, I don't know the instruction timings for any console or whatever. But I have a rough idea of if I see something that's like, I don't know, a visual sensor for an AI that's taking 2 milliseconds. Yeah, I know that's probably fucked. You know, I can kind of, that gut feeling is something that has to be confirmed. Don't just trust your gut. Never trust your gut. No, I'm not saying that you're saying that. I'm just saying that people should, you know, always measure, like always measure.
Of course. But it's just as a super basic frame of reference to get your head somewhere. Is this even fundamentally somewhere where it should be? Like you said, the UI update thing, that the Flash stuff, that doesn't necessarily just have to do with my experience. That anyone can imagine that the whole game to render, to simulate, whatever, takes 60 milliseconds, and just the UI, like the little marker of the enemy, the HUD, the ammo thing, and just that takes the same amount of time as everything else. That you have to see that there is something wrong.
Yeah, absolutely. So we have a question. Do you have any suggestions on how to get into performance optimization, apart from the 2 books I mentioned?
I guess what I would say is, I don't know, depends on if you have some code yourself or not. Just go in there, grab a random profiler, and start fiddling about, just getting the feel of it. If you don't have code lying around, then I would say start, for example, with a super simple naive particle system that you don't even need to add your renderer for it, just a simulation. And start by writing it in a naive code, in a naive way, with the have a particle class with a virtual update function. It doesn't really matter. And then use the profiler and let the profiler guide you through the transformation of that thing. And the reason why I say particle system is because particle system is one of the few things that is super easy to optimize, in the sense that there are no external dependencies. It's literally just that one little block of code that updates the particle that you can hammer on and hammer on and hammer on until there's no tomorrow. That is the easiest thing. The other thing that you could do is just grab a random project from GitHub to have some code and profile that. But it's probably better to just write your own simple particle system, simply because if you grab some random thing from GitHub, you don't know how it works, you don't know what it does. You might grab something that already is super optimized or that has some other issues that you don't know about. So yeah, it's probably easier to either grab your own code if you have something lying around, or write a super simple, again, I would say particle system, because that's just the simplest thing where you can train your profiling and optimization abilities from high-level architecture down to SSE intrinsics and multi-threading on top of that. You can do all of that just with a simple particle system. And I would say that is the thing. And you can start by just grabbing the profiler from Visual Studio. No need to get any other tool or do some instrumentation. No need. You can, once you're more experienced, you can get more of the some of the more advanced profilers like Intel VTune, which thankfully now is free for everybody. But you probably don't want to start with that because that might scare you away.
Yeah, honestly, like every time I've tried to use VTune, the manual is like 1,000 pages or something insane. It's like,
Yeah, it has a super steep learning curve, but yeah.
in terms of tools out there, it's never been easier to do profiling. There's multiple open source profilers. There's Tracy, which I think is one of the more popular ones. There's Optic. That's also another very kind of good one. This one I'm using at home. There's things like Superluminal, which is a really, really nice sampling profiler, which also works on consoles. And that one is available for a relatively cheap price if you want to just get a license home. I think it's on like $50 or something. I have no idea what telemetry costs, but frankly, like there's equivalent stuff to like telemetry out there that is, in my opinion, a better user experience. So yeah, if you want to profile, the Visual Studio profile is something I was using in the past. Although that kind of has some dependencies on your project, have to be compiled a specific way with some specific flags, because that one does inject into it. It does inject events into the code. So, but if you want to get started with something easy, Tracy, Optic are very fast and simple to get started with. Another point, with the particle system, you don't even need to render it. It can be entirely CPU based. It's a very good example like to use.
You really don't care about the graphics unless you're fancy and want to see something, but purely for practicing optimization and trying to use profilers and stuff like that, you really don't care about the rendering part.
Exactly. Is there any more questions? Oh, this is a good one. There's a comment saying that even in games, it drives me nuts when somebody points out you could do X to make that code faster. And I can see at a glance that that code is never going to be a performance concern. So this is super important. This happens all the time. People sometimes look at some piece of code and say, yeah, but I mean, we could do this more optimal. Yeah, this thing runs once in the frame and it takes like 60 micro. I have this other thing that runs 55 times a frame, and each one of those takes 50 micro. You need to pick your battles when optimizing. Never, this is to Severin's very, very first point, is don't randomly pick something and optimize it. Take a look at your frame, see what's the worst offender, and hit those. Like, I might write some really, really shitty code in one function that runs once a frame, and it might be super unoptimal and whatever else. If it doesn't show up on a profiler, there's no need to do anything with it. You know, if I have much bigger problems that are popping up, once I'm in a state where those things start popping up, yeah, we can optimize them. But again, if your UI is taking 16 milliseconds of the frame, you have bigger problems than saving a 20 micro somewhere.
Yeah.
You know.
Also, the other thing to note, but that is probably, I don't know if we do this again, but I'm happy to do it again with the rest of the agenda stuff. But it also depends. Like, it's not necessarily the biggest offender in the sense that the block that takes the most time that you need to look at. Because it could be that you have a main thread with lots and lots of super fast and tiny functions, but the whole block of main thread takes longer than your longest function on one of the workers. So you can optimize to no end that one slow function that is running on a worker, you will still not run faster because you're stalled by waiting for the main thread to actually finish the frame. So yes, you have to make sure to basically look at and optimize the right thing.
Yeah, so I think we're about an hour and a half. Yes, we'll definitely try to do a second part to this at some point. Maybe I'll even try to get some real examples of some captures or something just to give you an idea of how things work. I will do an animation stream that's a little bit more prepared with slides and stuff at some point. I'm kind of drowning at work at the moment, so I don't have much free time, which is why I figured this might be a fun thing to do in the meantime. You guys have my Twitter for the most part. If you want to poke me, or even Severin, I don't know if you use your Twitter anymore these days, but it's
I
linked
mean,
in the...
I use it to read, I never post, but I didn't do anything, so I guess people can tweet at me or however the cool kids call it these days. I don't know.
So your Twitter is, I think, at Direbrum still.
Yes.
So feel free to reach out to Severin or myself. And yeah, if you have any ideas for future streams or future topics or future like kind of chats like this, let me know and I can try to get people together that are experts in the field and have them kind of present their viewpoints and their thoughts and answer your questions. But yeah, thank you for joining us and have a great day. Thanks, Severin, for taking the time. And
You're
we'll
welcome.
see
No problem.
everybody next time we do this. So cheers.
Have a nice day.
All right, it's done. Yay.